Good morning, science-loving people, and welcome to my humble laboratory.
They could be watching at night and you're outside in their parents' yard, not in a laboratory.
It's morning now, and semantics. Either way, I would like to present you, the audience, with my 2-hour Hollywood production where I determine the mass of an electron using an egg timer and a ruler I stole from a first grader.
Heier explicitly said don't do any of that. Did you even read the instructions?
He did? After careful consideration, I have instead decided to test the acceleration of Earth's gravity by finding the relationship between the distance an object is dropped and the time it takes to drop that distance, using a ladder, a measuring tape, and a phone stopwatch. In this experiment, I will measure distances of 4, 5, 6, and 7 feet off the ground using the measuring tape. These values will be converted into metric later. I will then measure the time it takes for an object to drop these distances using the phone's stopwatch. And using these recorded values, I will create a graph that will help us find the experimental value for Earth's acceleration. So, here we have the ladder, and using this handy-dandy extendo ruler, patent pending, we can see the exact distances that mark 4, 5, 6, and 7 feet off the ground. Now, all there is to do is find an object to drop. I'm sure Shorty won't mind.
No.
How about this?
No. Are you nuts? Thomas.
One eternity later.
Fine. How about a tennis ball?
Yes, Thomas. A tennis ball is fine.
Now that that's settled with, let's get on to testing. As you can see, the distances have already been marked, so now all we have to do is drop and time this ball's demise. Now that we have this value, we need to carefully record it. Words cannot describe the danger of this part of the procedure, so we must give it the utmost care and caution.
Get on with it.
Tristan, this is a very precarious part of the procedure. One messed up digit and the whole thing.
As long as I'm getting paid by the hour.
I'll do this myself and spare you the boredom.
12 seconds later.
Okay, using these values, we can formulate a graph to find Earth's acceleration. Using the times we recorded, we can find the average time for each height, as seen on the far right of the data table. After finding the averages, we can create a graph using the distance as the independent variable, and therefore the x-axis, and the average time as the dependent variable, and therefore the y-axis. Once plotted, you can see that as it is, this distance in meters versus time in seconds graph isn't very useful because the slope curves, signifying that we would get a square root function. However, if we look at this kinematic equation, we can see that to get a by itself, while also adhering to the dependent/independent variable distinction, we need to square the average times and divide them by 2. Once this is done, you get these new values, which represents seconds squared. By plugging these new values into the y-axis, a linearized graph is created, and by finding the slope of the line of best fit, we also find the inverse of a, or the acceleration of gravity. However, without the use of a computer to determine the line of best fit or its slope, we can use the difference in the rise over run for the 5-foot and 6-foot points to get a fairly close calculated slope. As stated before, these slopes are the inverse of the acceleration, so by finding each slope's reciprocal, we can get the experimental value for Earth's gravity. In this experiment, I wanted to find the acceleration of gravity, and by using the wonderful Google, I have found the actual value of little g to be 9.81 meters per second squared. By finding the relative difference between the known value and my experimental one, we find that my experimental value had a percent error of about 2.5%, which is pretty good considering the amount of potential sources of error in my experiment. The most obvious sources of error is in the calculated time and distance, as I am not a robot and could be off by a relatively big margin due to my crude methods of measurement. But there are other factors as well, including wind/air resistance, which, however small, could potentially affect the tennis ball's descent, which would skew with my value of g. In the future, if I were to repeat this experiment, I would like to have more precise methods of measurement, including a slow-motion camera and something better than a measuring tape to calculate distance. I would also have my experiment occur in a closed environment, where I could apply a vacuum to remove any air resistance. However, I am not a rich man, and if you couldn't tell, I'm a high school student with a budget of less than nothing, and am currently in quarantine, and am forced to use the items already at my disposal, which doesn't allow for much in the way of precise measurement tools or vacuum chambers. So instead, I use cruder methods of measurement in less controllable environments. As a result of this poorly made YouTube video, I hope you can understand that the time it takes to fall x distance is equal to the square root of that distance times 2 divided by 9.81. I hope you found the information in this video educational or at the very least entertaining, and can use this information to do something good for the world, such as finding the time it would take to drop a piano on your annoying brother from your window.
What?
Yo necesito tu teléfono. Good morning, science-loving people, and welcome to my humble laboratory.
They could be watching at night and you're outside in your parents' yard. Yeah. Yard, not a lab.
Yes, I am out in the lard.
Cut.
Good morning, science-loving people, and welcome to my humble laboratory.
Sorry. My computer timed out.
Tell me when you're back. God. My phone, like, the storage is gonna be gone after this.
Delete your shit
No. Tristan! This is a very precarious part of the procediment.
then. It's okay.
The procediment.